Hi everybody, welcome to another video in Calculus 3, section 16.2, double integrals over general regions. Also previously, we have double integral over rectangular regions. So what is the difference? So the difference here is the integral where all of the limits are constant. This is called the rectangular regions. So in this particular case, y is between a and b, and x is between c and d. So we have a rectangular region here. Here we have more general regions, so there's no longer constant. Of course, they still can, but it could be anything. Right. So once again, you don't have to write out everything here. Just get the idea. Right? Pretty simple though. So there are two cases. The first one, those, and then the second case, those. So what is the difference here? So let R be the region bounded by above by the and below by those graph, and by the lines x equal to a and x equal to b. Right. So notice that whatever we put in the limits for the double integral, the outsides always have to be constant. The outside limit always have to be constant. The inside though can be function of the variable on the outside. So this one, because we have y in the inside, the limit will be y equal to and y equal to. So bounded by two function y equal to, two function of the outside variable. Same thing here, the dx is inside, so this is x equal to, and so the inner limit bounded by two function x equal to g of y and h of y. The function will be in terms of the variable on the outside. Right, so that's what the integral in terms of graph. The difference between those three and these three is that those two bounded by vertical boundary. Or horizontal boundary, depending on how you call it. It doesn't really matter. Just know that if it is consistently bounded by a point on a line, in that case, we can set up the limit so that outside will be a constant. The inner will be two functions of the outer variable. Once again, don't have to write out everything here. Just need to know that the outside limits must be constant, and the inner limit may be function, but that function have to depend on the outer variable. Fine. So let's look at this example. Express the integral as an iterated integral. So iterated maybe the double integral like what we have here, where R is the region bounded by the parabola y equal to 3x squared, and the bottom is, and 16 minus x squared. Right. Of course, we can graph these two functions easily, and we're going to graph that by hand too. Right, let's see the graph. Right, looks like one parabola here and one parabola on the top. Let's zoom out and see what happened. Right, so we have one parabola open up and one parabola open down. Look like there's the intersection. So let's just draw a sketch. Draw a sketch here. Right, the 3x squared is a parabola open up. And then the 16 minus x squared is the parabola open down. Right, so that is, let's just write y equal to 16 minus x squared. Right, first of all, we can find the intersection. The intersection, we'll just let this equal each other and then we solve for x. So 3x squared equal to 16 minus x squared. Move the x squared to the other side for x squared equal to 16. So x squared equal to 4. So x is equal to plus or minus 2. So 2 and minus 2. Right, let's set up the limits. Now, most important, do we do dx, dy, or dy, dx? Now, it's nice to know where we set up the function like this. Now, just look. Let's look in the y direction. In this case, we put dy in the inside. If we do that, we have the function below and a function above. If we look in that direction, that's what we have here. So we have one function above, one function below. So that looks good here. Now if you look on the side, if you look on this side, this is an eye, and if we look in that direction, we see it is bounded left and right. Above by the function y equal to 16 minus x squared, but below bounded left and right by the same function. So it's not very friendly if we do that, because on this one the boundary will be this one on the left, this one on the right, this one on the left, this one on the right. Meaning on the left the boundary is not come from one function, on the right boundary not come from one function. We never want to, we try to avoid this. Unless we have to, we have to set up the integral. But you see what we have here. One boundary on the top, one boundary at the bottom. One on the left, one on the right. So if we just have that, then we have one integral. So we prefer to set up the integral that way. So this will be a double integral for sure. And then we looked which way, which perspective give us one boundary on each side. We see in this direction, one on the top, one at the bottom, which is good. So we just write two functions bounded below by y equal to 3x squared and bounded above by y equal to 16 minus x squared. And here we just have the function in the middle, the integrand. Now, since we have set up the limit between by two y function, so we're going to do dy and then dx. So the double integral, the inner function, the inner can be bounded by two functions of the outer variable. So that's perfect there. And x values go from -2 to 2. The outside will be just constant. The outside must be constant. So -2 and 2. So that integral for this region. Right. So once again, the outside must be constant. The inside can be two functions of the outer variable. So if we want to be very specific, we said inside will be y between those values and outside between these values of x. Right, so like that. Later on we will evaluate the integral, but the most important thing here is how to set up the integral. Right, next, write. Sorry, that's the next page. Wait, this is the next page. Find the volume of the tetrahedron, which is the pyramid right here. In the first octant, our first octant will be by the coordinate plane x equal to 0, y equal to 0, and z equal to 0. So we have that. And assume a, b, c are positive. So, first of all, remember we did set this on the first section. Analogy to the area under the curve is the volume below the surface. So that is exactly what we have here. If we want the volume will be between the surface z equal to c minus ax minus by. So that will be the function. So if we want to set up the integral, just give a bunch of space here, because we're going to need a lot of space. But we don't know the function in the middle, the integrand. So the area will be between, the volume will be below this surface, z equal to that. So that is the integrand. And now do we set up dy dx, or do we set up dx dy? Right. In order to do that, what we have to draw is in the xy plane. Everything on the xy plane. Now if we just project this graph onto the xy plane, on the xy plane we will have that. So on the x-axis it is c over a, so let's about say here, and on the y-axis is c over b. And we'll talk about this one. Right, now actually this one we can either set dx or dy, because if we look from left to right, oh, by the way, in terms of the limit, so this one is above, plus the one that is below, and then on the right, and then the left. So the limits, yeah. So we go in the positive x-axis from left to right, or from bottom to the top. Either way, for this triangle, we have one boundary on each side, bottom and top. So in that case, we can set dy dx, and also left and right. So we can also set dx dy if we want to. So either dy or dx in the middle will be perfectly fine. Like I said, when all things all being equal, just going to put dy dx. Simply because the x I want on the outside, because after all said and done, it will be nice. Alright, so first of all, what is this equation? What is this equation of the line here? So we look at this equation of the plane. On xy plane, z is equal to 0, right? So this is where z equal to 0, where we are on the xy plane. So we have c minus ax minus by equal to z, but z is 0. Now we can solve for y in terms of x, because since we put dy in the middle, this has to be the limit of y equal to. It could be a function of x, and on the outside will be x equal to, and x equal to. The outside must be between two numbers. Inside will be between two functions. So I moved by over equal to c minus ax, and then divide by b on both sides. So y equal to c over b, which is the y-intercept, minus a over b x. Right. So that is the equation, and I'm going to put that. Now, let's look. If we put dy in the middle, that means we're going to look in this perspective along the y-axis. So if we put dy in the middle, once again, if we put dy in the middle, we're going to look along the y-axis. At the bottom, we see this function, which is y equal to 0. And on the top, we see that function. Alright, try to write very small because we need to integrate. And then x, the outside will be just on the x-axis now. will be between those 2 points, will be just 2 constant and go from 0 to c over a. Right. Try to write very small because we might not have enough space. So our outer limit is still the same. Now we integrate the inside function with respect to y, so everything else is constant. So we will have cx minus ax, I'm sorry, with respect to y, right? So cy minus axy minus b y squared over 2. Limit y equal to 0, y equal to c over b minus a over bx, and then dx. Right. Notice all of them have y. When we put in 0, we're going to have 0. So only the upper limit has some values. Right, we'll put that in for y. Put that in for y. And that in for y. Say 1/2 b right. I try to multiply it out, and so we have c squared over b minus ac over bx minus ac over bx plus a square over b x squared. Right, I multiply this out first and then multiply by 1/2 b. Actually, the answer is very easy to verify, so we just need to, so I know what the answer is already, but just be careful here. Right, square is multiplied by itself. Right, multiply this, we have c squared over b squared. B and b cancel out, so we have negative 1/2. B cancel on b, so we have c squared. B and b cancel out. Right, now we multiply this, 2 will be cax, and b squared at the bottom cancel with this. Oh, so there's a minus here as well. So we have I just write it down. I multiply this 2 will be a c x b squared, and multiply by negative 1/2 b. Oh, b on the top, sorry. That cancel with b squared, so we have negative 1/2 and negative, actually that's the plus. 1/2 acx, ac over b times x. and then multiply this 2. Will be negative negative, so that is positive 1/2 b acx over b square, cancel square would be, so we have 1/2 acx over b. Those two should be the same. And then finally negative those two terms, negative 1/2 b a square over b square x square, b and b square cancel, so we have negative 1/2 negative 1/2 b and b square cancel, so we have a square over b x square. And then dx. Sorry, that is 1 over 2 a square over b x square. Right, a lot of things that are equal. Once again, I apologize for running out of space here. So combined like terms, there are a lot of x terms with x. But the only term that have no x is this one, so we have c square over b. And then let's see, this term are the same, ac over bx, ac over bx, and then ac over bx, so what do we have here? There's negative 1, negative 2, and those are plus a half, so plus 1, so that's just minus ac over bx, and then the square terms be this one, sorry, those two are the same, right? I forgot. 1 minus 1/2 is 1/2. Those two, subtract that, and what's left is the square terms. We have 1 minus 1/2, so it's 1/2 a square over b x square. Dx. Right, finally we can integrate. There's no x here, so we just c square over 2b, stick an x to it, then minus 1/2. There's an x here, so it will be x square over 2, 1/2 ac over b x square. And then plus 1/2, and then x cubed over 3 a square b x cubed over 3, going from 0 to c over a. So we run out of space, so let's continue over here. Hopefully will be enough. Okay. Right. So again, if we put in 0, there's nothing. If we put c over a, we have 1/2 c cubed over ab. And then minus 1/2. Put ca in here, we have c cubed, let's just write ac over b c square over a square. cancel out the square with a. We have c cubed over ab minus 1/2. And then we have plus 1/6 a square over b. And then c over a is x, so c cubed over x cubed, c cubed over a cubed. So where we simplify, we have 1/2 c cubed over ab minus 1/2 c cubed over ab, and that is plus 1/6 square cancel out, and also c cubed over ab. Cancel this out. The answer is 1/6 c cubed over ab. Alright, sorry, kind of run out of space, but that's what we have, and the answer is correct. Let's just confirm that using geometry here. So what we have, sorry, the perspective is bad. Let's look at that again. Let's look at this. We have one side here. The length is 0 to c over a, so this length is c over a. And the length here is c over b. This is the right triangle, so the area of this triangle is 1/2 base times height. So this is 1/2 c squared over ab. So that is the area of the base triangle. And then if we have the pyramid, the area of the pyramid is 1/3 base area times the height being c. So we have 1/3 times the base area times the height. Sorry, 1/3 base area times height. The base area is this times the height is c. So we have 1/6 c cubed over ab. So that's exactly what we have, c cubed over ab. Right. Actually, this is not as complicated. Just because we don't have a lot of space, it makes it a little more difficult. But that's how we evaluate it. Right. So once again, the inside limit can be two functions of the outer variable. The outside limits are two constants. Right. Try another one. Find the volume of the solid bounded by the surface below the surface 2 over 1 plus y above the xy plane. So from the xy plane to that function. So the integral two plus 1 over y. Right, where they will set up the y over the x, that to be determined. Let's just graph. Line y equal to x. The line y equal to a minus x, meaning when x equal to 0, y equal to 8, and when x equal to 8, y equal to 0. And y equal to 1. So the intersection of this, of course, is the triangle here. So the question is, should we set up dx or dy, dx dy or dy dx? So let's look at it's just a matter of perspective. If we put dy in the middle, meaning we're going to look along the y-axis. So we'll see this function at the bottom, this function on the top. So we're going to see that. And this is the big problem, because at the bottom it is bounded by the function here y equal to 1, which is good. But on the top it is bounded by two different functions. Because of that, if we set up this way, we have to have two integrals. And I don't want to do that. So let's switch things around. Let's look in the other direction. Let's look in this direction along the x-axis. On the left we see this function, and on the right we see this function. So one boundary on each side, that's perfect situation to have for one integral. So on the left is bounded by this function, on the right by this function. So since we look along the x-axis, this is going to be dx, and this is going to be the function in terms of dy. So on the outside y is constant. So let's look at the limit. The intersection here look like x equal to 4, y equal to 4, right? We can find the intersection of these two functions easily, 4 and 4. So this point is 4 and 4. So if we put on the y outside, the limit will be determined by two numbers from 1 to 4. So that's easy. But the limit in terms of x though, I mean the limit x equal to, so we put the x inside because we look at the x-axis, look along the x-axis, one on the left, one on the right, and the left function is x equal to, the right function is x equal to. Right. Now if it's x equal to, the equation should be x equal to, right? Now y equal to a minus x, this is equivalent to x equal to a minus y. Yeah, so we have to write in terms of x equal to y equal to x or x equal to y. Those two are the same. So because we set up the x in the inside, we look along the x-axis, the boundary must be function x equal to. And so we see on the left it is by this guy, this function. So from left to the right. And then we set up the limit for y on the outside. Y will be just on the y-axis. It is between 1 and 4. So y equal to 1 and y equal to 4. Right, let's just integrate this quickly. Right, notice that this with respect to x. So the integral here is easily done. It's just constant, right? There's no x in here, so it's just a constant. And evaluate from x equal to y. I mean, just a constant, and then times integral with respect to x. So there's an x here. Sorry, forgot. Integral of the constant is the constant times x. Then going from x equal to y to x equal to a minus y. And then we just have dy. Right. Y equal to 1, y equal to 4. Right, to put in the upper limit. I'll put in for x, a minus y. And put in the lower limit. X equal to y, so just y. Right, let's multiply it out. 2 times 8, 16. 2 times y. 2 times minus y. So that's 16. 2 times y, sorry, minus 2y. And then plus a over y. And y minus 1. 1 cancel out. Minus 2 times y, and minus 1 cancel out, so that's just minus 1. Right, so 16 minus 2y, a over y, minus 1, minus 2y, minus 1. Right, 16 minus 1, so 16 minus 2 is 14. Minus 2y, that's minus 4y. And then plus 8 over y dy. Now we integrate. Be 14. Integral, there's a constant, so will be just y minus 4 y squared over 2. And this is integral 8 over y is 8 ln of y. Evaluate from 1 to 4. So put in 4, we have 14 times 4 minus 4 over 2, cancel out to have 2 times 4 square plus 8 ln of 4. And then subtract, we're going to put 1 in, we 14 minus 2, because y is 1, so it's just 1, and then plus 8 ln of 1. ln of 1 is equal to 0, so this is equal to 0. So 14 times 4, 56 minus 16, 16 times 2, 32, plus 8 ln of 4 minus 14 minus 2 is 12 minus 12. So 56 minus 32 minus 12, so that is 44. 56 minus 44 is 12. Right. For this one, of course, we can just check. Right, let's go from 1 to 4. The integral, I will start from all the way from the beginning. 2 plus 1 over x. I use x instead of y. Times 8 minus x minus 2 plus 1 over y, 1 over x times x. I close x. So about 23 point something. How about 12 plus 8 ln of 4? Yeah, so look like we do it correctly. Right, so the point here, of course, is set up the limit. The reason we put x in the middle because we look along the x-axis, one function on the left, one function on the right, so we need only one integral for that. And in the middle is x, so we have x equal to, x equal to. Both of them are function of y, the function of outer variable. So that's what we have. Right. So write the integral that calculates the volume of the solid bounded by those two functions. Now we have two different values of z, but it won't be that hard. On the top we have z equal to a minus x squared minus y squared. At the bottom we have z equal to x squared plus y squared. So we set up the limit. the volume will be bounded by these two functions. The function above is going to be 8 minus x squared minus y squared. I'm just going to write this area. We're not going to evaluate this. Evaluate this involved in actually the next section. We can do that nicely, but not in here. So function above minus function below, in that case 3D, is x squared plus y squared. Right, so we set up dx or dy, but we know that the difference in the y is between those two functions. So what is the intersection of those two? Alright, let's say both of them equal to z, x squared plus y squared equal to 8 minus x squared minus y squared. Move everything on one side. I mean x squared and y squared. We have 2x squared plus 2y squared equal to 8. So give us x squared plus y squared equal to 4. Now this is a circle of radius 2, center x 0, 0. So we talk about this circle. So if we don't know how to set up the area for the circle, for now we can just say dA, and on here we just draw a circle of radius 2. And this is a case of a picture tells 1,000 words. So that perfectly describes what the region that we will evaluate over. So we just write dA. If we're not sure about the x or dy, we can just write dA, and the region of a dA is that disk of radius 2. Right. Now if we want to go through specific of do that to do y dy dx or dx dy, we actually can solve for y. Y squared equal x squared plus y squared is 4, so we can get y squared equal to 4 minus x squared. And take the square root on both sides, we have y equal to plus or minus square root of 4 minus x squared. So because there's plus or minus, one positive, one negative, the positive is the one above. So that part above is y equal to positive square root of 4 minus x squared. The one below is y equal to negative square root of 4 minus x squared. The positive on the top, the negative at the bottom. That makes sense. And then so that would be the limit, because that both function of y, we're going to put dy in the middle. Of course, if we solve for x equal 2, we're going to put dx in the middle. But because this time we have two functions of y, we're just going to say the limit between two functions of y. Like I said, we're not going to evaluate this here, but the next section we can do this in a few steps. For now, just set up the limit. And then the limit on the x, so this is dy dx. The limit on the x will be just negative 2 to 2. Right, the inside we have 8 minus x squared, so we have 8 minus 2x squared minus y squared minus y squared minus 2y squared. Right, let's just set up the integral as so as to be. We just leave it at that. Right. Next, find the area of the bounded. The area bounded by these three functions. So up to this point, what we have is a double integral with a function inside. So that we calculate volume if we just bounded by the volume. Which one's that? Right. So like the volume below the surface. If we have the equation of surface, put it there, we have the volume. Now, if we don't have anything, we just do the like this. there's no function, the integrand is equal to 1. When we do this, what we have is the area of the region R. Right. Once again, if the integrand is 1, what we calculate is the area of the region itself. So that's a nice way to evaluate the area. So find area bounded by this function y equal to x squared. Of course, we're going to draw x squared y equal to negative x plus 12. So when x equal to 0, y is equal to 12. When x equal to, let's say, 2, then y is equal to 10. So yeah, so this graph's not long enough. Yeah, so there's the intersection here. And then y equal to, for x plus 12, when x equal to 0, y equal to 12. When x equal to 1, and that's going to be 16 way up there, so it's not good. Choose something negative. How about x equal to negative 2? Put negative 2 in here. That's negative 8 plus 12, so it's 4. So yes. So. Negative x plus 12. As we're talking about that. Now, it's a bit complicated here. If we look in this direction, meaning that we're going to have dy dx. I'm sorry, dx dy, because if we look along the x-axis, there'll be dx dy. So on the left is by this function, but here the boundary change on the right from there to this function, and then here we have boundary changing again. So on the left there are 2 boundary, on the right there are 2 boundary. If we're going to set up the integral, there will be 3 of them. The first integral is here, the left and right by those 2 functions. Next, this region here, left and right, and at the bottom, left and right. So if we set up the x dy, we need 3 integral for that. Now how about if we look along the y-axis? If we look along the y-axis, meaning it's going to be dy dx. So it will be that direction. Yeah, still a bunch of boundary, but a little less. On this region here, above by that function, below by this function. And on this region here, above by that function, below by this function. So if we set up dy dx, we have, if we set up dy dx, there are 2 different boundaries. Again, 1 and 2. So there will be 2 integral. If we set up the x dy, there will be 1, 2 boundary changing, and 3. So if we set up the x dy, sorry, long one. there'll be 3 integral. And of course we go with the one that take less than that, less integral. So we're going to be dy and dx. Right, first it's going to be for this here. And since we find the area, the integrand is 1, so there's nothing here. We just write dA or dy dx or dx dy. And since we look along the y-axis, this is going to be dy dx, where y values bounded above by this function. Once we get used to it, we don't need to write y equal to. When we see y inside, that have to be y equal to. But the bottom is parabola y equal to x squared. The boundary here, right? So what is the boundary? Y equal to x squared, and this. So there's two functions. Y equal to x squared equal to 4x plus 12. Move everything on one side. Become minus. So we have x minus 6, x plus 2 equal to 0. So x equal to 6, x equal to negative 2. So this is negative 2. That is the limit for x from negative 2 to 0. So that one integral. That one. Now we go to this one. Once again, it is dy and then dx. The integrand is 1. So if we want the area, we're just going to put 1 there. And this one dy dx. The function above is negative x plus 12. And y equal to negative x plus 12. And the function below is y equal to x squared. The limit for x though go from 0 and the intersection here look like x squared equal to negative x plus 12, or x squared plus x minus 12 equal to 0. That gives us x plus 4, x minus 3. So x equal to negative 4 or x equal to 3. So that is the integral. Once again, from negative 2 to 0, x squared for x plus 12 dy dx, plus integral from 0 to 3 x squared negative x plus 12. I said when it's clear to the we just drop the y and x equal to, just write the limits. To evaluate this integral should be easy. So I'm just going to leave that it here. Of course, if we go way back to calculus 1 or calculus 2, we just say the function above minus the function below. Actually, I'm just going to do one step. There's nothing here, right? The integral of 1 is y. Integral of constant is just that variable. And then we just put that in here. So now this makes perfect sense, consistent to what we have in calculus 1 or calculus 2. We just have the function above minus the function below. The function above minus the function below. Function above minus the function below. And integrate those two. That should be easy, so I'm not gonna we don't need it to finish that problem. That should be easy. Alright, so yeah, Sometimes we, of course, ideally we want to just have one integral, but in this case we cannot, so we just have to do a split. Right. Now next one is interesting. Sketch the regions of integration, reverse order of integration, then evaluate. So first of all, I think I mentioned this. Actually, no, I didn't. I think we mentioned previously on the previous section, when we have something like this, we cannot integrate. So the answer is not going to be anything nice and easy. So we're just going to have that. You cannot do it. Same thing when we have sine of x squared. You cannot do that either. Actually, there's some name for it. This one is called the integral sine and integral cosine. The result is, this is, I think, is the Fresnel, if I spell this correctly. And we define this to be the Fresnel sine function. And this is the integral sine, integral cosine. So because they have a special name for it, which means it's not going to be anything nice and even. So, and at this point we can only do anything that is nice and even. So there must be a different way to do that. If we evaluate in this order with respect to x, we cannot do that. Simply just can't. Right, so let's just sketch. Right, so we put the x in the middle. That means the y here is x equal to y and x equal to square pi. Now the outside is y, meaning y equal to 0, y equal to square root of pi. So let's say on the graph, let's see, 1, 2, 3, 4, 5 is square root of pi. It's about there. 1, 2, 3, 4, 5. Right. Now, the x in the inside, right? Meaning we're going to look in the x direction. First thing is x equal to y. We're going to draw that equation. X equal to y or y equal to x. X equal to y. So the first thing we see is from the left is that one. And on the right we see is x equal to square root of pi. So if we look in along the x-axis, that's what we see, right? From left, x equal to y, to the right, x equal to square root of pi. And then y values indeed go from 0 to square root of pi. So there's nothing new there. So we're talking about the triangle here. Now they said we need to reverse the integral. So this integral should be reversed. Whatever we reverse, we cannot just reverse the limit. That would be totally wrong. Why we cannot do that? So here we have those are, let's say if I just reverse them, dx dy, let's switch to dy dx. Limit for y is 0 to square root of pi, and limit for x is y and square root of pi. The problem here is the outside limit always have to be constant. So if we just simply switch them, it will not work. Because the y go the outside like this, we cannot integrate something like this. Besides, that's totally wrong. So, meaning we have to set it up again. Now let's look. If we put dy in the middle, the function, the integrand is still sine x squared. Now if we look along the y direction, what do we see first? We see this line first, right? Y equal to 0. And then see this line, x equal to y, so y equal to x. So we have, if we put dy in the middle, there are two functions of y. And then the limits on the outside for x, from x just 0 to square root of pi. Those are limit for x. They'll say, yeah, it's not a big deal, right? So how did that help? First, as mentioned before, this function we cannot integrate. But when we write like this, we can integrate. Why did that help though? Right. Sine of x squared is constant with respect to y. Integral of the constant, we're just going to multiply by y. Right? Integral constant is a constant times the variable. And we go from 0 to x. Put in x, put in 0. Right. Once again, we should write smaller because we might not have enough space. Right. Put in x, we have sine of x squared times x. And this x makes the whole things a lot easier. We can use substitution if there's an x here. And then we subtract where we put in 0. And that is 0. So we will have x equal to 0, x equal to square root of pi. Here we just have x sine of x squared dx. That is a lot better. What is x? Now that's just a simple substitution. Right, substitution. I'm going to let u equal to x squared, and we solve for dx. So let u equal to x squared. So I'm going to get dx, meaning we have to take the derivative with respect to x. Move the dx over. And then divide by dx. Divide by 2x, sorry. So we have u and dx. And then also we change the limit. When x equal to 0, when x equal to 0, u is x squared, so 0 squared is still 0. When x equal to square root of pi, u is x squared, square root of pi squared will be just pi. So this integral equal to, since we change the limit to u, I'm going to say u equal to 0 to pi. U equal to 0 to pi. Equivalently from 0 to square root pi for x, 0 to square pi for x, 0 to pi for u. And then we have x sine of x squared, which is u. And dx is du over 2x. X and x cancel out. The 2 on the outside. So that's 1/2 integral from u equal to 0 to u equal to pi sine of u du. Integral of sine u is negative cosine u. U equal to 0, u equal to pi. So we have 1/2 negative cosine pi minus 1/2 negative cosine of 0. Cosine pi is negative 1 and cosine of 0 is 1. So we have 1/2 negative 1, so that's just 1/2, and minus negative 1, so that's going to be plus 1/2. So this is just 1. Alright, let's check real quick. I'm going to enter from this step of that 0 to square root of pi, and the integral x times sine x squared x yeah, we're good. Alright, next example. Set up the limits for integration using both dx and dy, dx dy and then dy dx. Right, we just need to set it up here. We not evaluate this integral. Right, so first let's graph a bunch of those functions. The scale is not going to be very good on this one. Y equal to e to the x. I said the scale is kind of bad here. If 0 is equal to 1, so we know it's going to be like this. Y equal to 1, so this is y equal to e to the x. Y equal to 1, horizontal line. X equal to 4, vertical line. Let's say 1 here and 4 here. I said the scale is way off. Don't go by this point. This point is not 5, obviously. The scale is very bad here. Sorry about the scale. Because if you write e to the 4th power, so that is 54. So this will be way up there. Right. So the scale is, once again, the scale is not good here. But we're talking about this region here. Right, intersection. This is when x equal to 4, right? When x equal to 4, this point is x equal to 4. And the function is y equal to e to the x, meaning e to the 4. So the point there is 4 and e to the 4th. We have the point here and here. Now set up the limit, dy dx and dx dy. So let's just say this integral on this one we're going to do, let's do dx dy first. Meaning that in the middle, if we put dy dx in the middle here, this have to be two function of x equal to. And dx, meaning we look in the x direction. What do we see first? What equation do we see first? Oh, this one. And we see second is that line. So we know it's going to go from something to 4. Now what? Remember, this equation is y equal to e to the x. We need to write equivalently x equal to. So what is the inverse function of e to the x? And then if you remember, that will be ln of x. So let's solve for that quickly. If we have y equal to e to the x, we can take ln on both sides. ln and e cancel out, so we have ln of y equal to x. So on the left, it is bounded by this function, x equal to ln of y. On the left and on the right, it is bounded by x equal to 4. So that's the limit for x. The limit for y, the y values will go from 1, y equal to 1, to all the way here, which is e to the 4th. So that will be the limit. Right, let's draw this again. This time we do dx, dy dx. 1, 2, 3, 4. Right. Now we will set this limit. Yeah, the function in the middle is unchanged, but the limit here is going to be dy and dx, meaning that we're going to have dy in the middle. The inner function will be y equal 2. Then on the outside it will be x equal 2. So it's inside out. Right. See, if we put dy in the inside, meaning we're going to look along the y-axis. If we look in that direction, we see this line first. The equation is y equal to 1. And then we're going to see this line, this curve, y equal to e to the x. If we look along the y-axis, that's what we see. On the x-axis, it's just from 0 to 4, so that part is easy. Right. Now if you evaluate these two integrals, you should get the same thing, because describe the same region. Right. Once again, we may have some function inside. If we don't have any function inside, what we do is we calculate the area of the region R. Right, now do the same thing for this function. Y equal to sine x, y equal to 0, and x equal to pi over 2. Right, y equal to sine x. I'm just going to draw in one quadrant. Just say here. Y equal to 0, that is the x-axis. And then x equal to pi over 2. So we have the graph. Sine of 0 is 0. So let's just draw a few points. 0, 0. This point, sine pi over 2 is 1. And sine pi is 0. So here we have x equal to pi over 2. So it will be here. Right. Once again, we're going to set up both dy over dx and dx over dy. So if we're going to go with, let's do this time dy over dx first. The function in the middle, the integrand, doesn't affect much, doesn't do anything to the limit. Right, let's put dy dx first. So dy in the inner function, in the inner integral. So the limit will be y equal 2. And by the way, what is the region we're talking about? Bounded by those three functions. So I see is this part here. Now if we look along the y-axis, because we put dy in the middle, dy in the inside. It's bounded below by y equal to 0 and bounded above by y equal to sine x. Yeah, so bounded by two functions y equal 2. If we put dy in the inside, on the outside is x, we go from 0 to pi over 2. Right, I try the same thing here, but this time dx over dy. X equal to pi over 2. And then here y equal to 0. Yeah, so those are the three functions. Once again, the region is still talking about that, but this time going to be dx and dy. The integrand is unchanged. Limit. Now since we put the x inside, will be bounded by two functions of x, and on the outside will be bounded by two constant y equal 2. Right, let's just write out the point 0, 0, pi over 2, and 1, pi and 0. Right, so we look in the x direction. We're going to see this sine curve first, and then we're going to see the vertical line. So from left to right is that. But we have to write as x equal to, if y equal to sine x, this is equal to x equal to sine inverse of y. And we go from sine inverse of y to pi over 2. Again, left to right, bottom to top, and then the limit on the y values go from 0 to 1. Yeah. Again, when we interchange the limit, we cannot just interchange. When we interchange the order of integral, we cannot just switch in the limit. It will not work. We have to draw it out and then change accordingly so that the outside are constant, the inside are function of the outside variable. So this is very consistent here. Right. Last example. Reverse the order of integration. Wait a minute. Right. First of all, when you look at this, you say, this is dA. So is that dx or dy? I mean, is that dx dy or is that dy dx? How do we know? The outside function, the outside constant, won't be able to tell much. But here's the clue. If we write it is a function of x, meaning the x has to be on the outside, right? The inside integral will be in terms of the integral of the outside variable. So dx is going to be outside. If dx is going to be on the outside, meaning dy is going to be in the inside. And this will make perfect sense that if we have dy in the inside, it is bounded by two functions of y, square root of x and 2. And then on the outside, we just have x equal to 0, x equal to 4. So even though it's not specified if this is dy dx or dx dy, we know for sure it has to be dy dx because of square root of x here. Whatever the function of variables, that variable will be on the outside. So dx on the outside, right? So now this will be easy. Y equal to square root of x. I'm just plot a few points here, 0, 0, 1, 1. Square root of 4 is 2. So if we have dy in the middle, that means we look in that direction. We see this curve first, and then we see y equal to 2. So talking about this region here. Yeah. Equal to 2. Right, so we're talking about this region here. Yes. Right, and indeed, of course, after that we have x from 0 to 4, which is good. Yeah, from 0 to 4 on the x-axis. Now let's switch this to dx and dy. Now if we put dx in the middle, and then dy. If we put dx in the middle, we will look in this direction. We'll see first is this line, which is the vertical line, the y-axis. The equation is x equal to 0. So first we see is x equal to 0 on the left, and on the right we see that curve. The equation originally was y equal to square root of x, but since we write like this, we need the function x equal to. Right, if we want to solve for x, why don't we just square both sides, y squared equal to x, or x equal to y squared. So that will be the limit for y. I mean, limit x equal to y squared, limit two functions of x on the left and on the right. X equal to y squared. Looking from the left to the right. Right. And finally, the y values on the y-axis only go from 0 to 2. Right. This one we don't have the function, we cannot really integrate. But to switch the order of integral, that's what we can do. Right. Once again, double integral dx dy, dy dx doesn't matter. If we have dx in the middle, in the inside, we have x equal to as the limit in the inside. And those x equal to can be the function of the outer variable in terms of y. And if we have dy dx, inside we have bounded by two functions of y equal to, and the function could be in terms of x, the outer variable. So that will be very consistent. Outside limits always constant. Right. So that's what we have for this section. As always, thank you for watching.